Hi everyone, and welcome to this tutorial on how to spawn enemy waves in Godot 4 and C#. And just before diving in, I want to thank @MollyMoose, I hope I'm pronouncing it right, whose comment actually inspired this video. So if you too have some neat Godot concepts that you'd like me to do a tutorial on, feel free to suggest one by dropping a comment down below. But anyway, by the end of this video, you'll know how to spawn enemies at regular intervals according to some predetermined list, how to make them walk along a simple top-down path, and how to check if the wave has ended. So you should have all you need to set up one of the core features of a basic tower defense game prototype. Of course, don't forget that if you want to get the files for this tutorial directly, you can have a look at the GitHub repo with all my Godot tutorials over here. And as usual, since we'll be coding our logic in C#, make sure that you have a version of Godot with .NET enabled. But now, with all that said, let's dive in and discover the basics of creating enemy waves in Godot and C#. Okay, first things first, we're going to implement some logic to tell our wave manager script what enemies we want to spawn in each wave and in which order. Note that in a real tower defense game, you might want to generate this order procedurally to allow for endless modes. Still, oftentimes, those games also rely on some specific ordering of the enemies in the wave to create a steady rise in difficulty and present the player with an interesting challenge. Also, in this tutorial, I'll once again use some really cool assets made by Kenny. And as usual, if you want, you can also go to his website and browse his whole free library of CC0 resources to find the packs that you prefer. But alright, so let's say that here our prototype contains 3 types of enemies: the whites, the blues, and the reds, from the weakest to the strongest type. We'll start simple, and inside the scene, we'll attach a new C# script on the root node to handle our enemy waves called the Wave Manager. Inside this script, the first step will be to define our 3 types of enemies by creating a simple data structure called enemy data and creating a list of enemy data instances. Don't forget that the list type in C# requires that you import the system.collections.generic library. Now, of course, in an actual game, this data structure would contain a lot of things, but here we'll just consider that our enemies are defined by their visual sprite, their health points, and their speed. So inside the list, we create 3 instances of our data structure, one for each enemy type, and set up some arbitrary values to get more or less powerful enemy types. As is often the case in tower defense games, I'll say that stronger enemies have both a higher value for health points and a higher speed. The next step is to use this data to actually spawn units, according to a wave list. Meaning that we want to tell our game what enemy types to spawn for each wave, so how many to create and in which order, and then use these simple predetermined lists to feed our scene with new enemies regularly. So to begin with, let's define these wave lists. In this tutorial, we'll consider that we have 4 waves of increasing difficulty. And to specify our lists, we'll create another list that takes in C# tuples. Now, if you're not too used to those, C# tuples are a really cool built-in tool that let you bundle multiple chunks of data together as a single variable, typically to return several pieces of info from a function or to create pairs of numbers, like here. In our case, our tuples will contain 2 integers, because we'll first give the type of enemy to spawn, so 0, 1 or 2, and then the number to spawn. So for example, the first wave will contain 5 whites, then 3 blues, and then 2 reds. Similarly, we can create a longer wave 2 by spawning the same types in the same order, but with higher counts, or even more complex waves 3 and 4 that intertwine the types of enemies. We could obviously also just use lists of integers, where we repeat the enemy type to spawn again and again to show how many instances we want. But this would be way more annoying to read and maintain. Anyway, with this data ready, we can now spawn our enemies periodically to gradually fill the level with our wave. To create our enemy units using our wave list, the idea will be to use a timer node to regularly move forward in our reference list and instantiate the given enemy type in our scene. This is quite straightforward, though a nice trick we can use to make it even easier to keep track of where we're at in our wave list, especially since we haven't just written out the list as a simple list of repeated integers, is to first pre-compute this equivalent representation for the current wave and then iterate through this temporary data. So let's say that in addition to a reference wave list, we also have a list of integers with the current wave data. Then when we start a new wave, we'll go through our base wave list that corresponds to the wave index, and for each tuple, spread it as a repetition of integers in our temporary list. For example, at the end of this for loop, my 1, 5 tuple will have become a series of 5 ones one after the other in the wave data list variable. Finally, we just need to prepare an integer to keep track of where we're at in this simple list that is reset to 0 when we start a wave. And also we'll have an exported variable of packed scene type to reference the enemy prefab scene I prepared beforehand and that we will study in more detail in the next section. To actually see the exported variable in the inspector, don't forget that because we're using C# and not GDScript, we need to recompile our project. And then we can just drag our scene in the slot to reference it in our script. Okay, so we now have all we need to actually trigger the periodic spawn. To do this, let's start by adding a timer node in our scene under our root node. We can increase its wait time a bit, for example to 2 or 3 seconds, to have the enemies spawn a bit less frequently. And then in our C# script, we'll prepare a callback function called onSpawnEnemy, recompile our project so that Godot knows that it exists, and link it as a callback for the timeout signal of our new timer node. We'll also get a reference to this timer node from the scene in our script so that we can start it when we start a new wave. Now, in our onSpawnEnemy function, we will just pick the enemy type at the current position in our wave data list and increase our position for the next time. Of course, we should also make sure that this position is within the bounds of our list, or else abort early with a conditional return at the top of our function. Then we'll instantiate our enemy scene by calling the instantiate method of our packed scene variable and add it as a new child under our enemies node. We'll also make sure to get it as an enemy script instance so that we can call its initialize method with our enemy data values, the sprite, the health points, and the speed. Again, we'll talk about where this function comes from in just a second. Also, of course, to optimize this, it's better to cache the reference to the enemies node at the very beginning of the scene, since it never changes, and we'll be calling this onSpawnEnemy function quite a bit. Of course, you could also export the variable and drag it to the inspector like we did before if you prefer. Now we'll also see that in our ready function we trigger the first wave automatically, and in our input function override, if the player pressed the spacebar, we will trigger the next wave. Here I'm using another counter to know what's the index of the current wave, and to keep things simple, we won't bother checking if we are already currently running a wave, though obviously in a real game, we'd need to do that. Okay, so if we run the scene at this point, we see that after a few seconds have elapsed, an enemy pops in the scene, but it's in the top left corner. So after a few additional seconds we get another one, and then another one, and if we wait for a while we see the enemy type eventually changes according to our wave list, but still all the enemies are packed together at the exact same spot and they don't move. So now let's discuss how to have our enemies move and follow a specific path so that they actually fill the level as time goes by and we get more of a tower defense-like setup. For now, when our enemies spawn, they stay still at the exact same spot in the top left corner of the level, and so they all appear on top of each other. What we want to do here is define some path for them to walk on, and so we want them to go from a spawning point on the left to the exit point of the level on the right. Luckily, for this, Godot has a great pair of tools called the path and path follow nodes. Those exist both in 2D and in 3D, and today we'll focus on the 2D version. The gist is to first use the path2D node to define a curve of points that can either be a straight line or a more snaky shape, and then we need to create a hierarchy like this one with the path2D node at the top, the pathFollow2D node inside, and the object we want to move inside again. At this point, just by selecting the pathFollow2D node and going to its inspector, we can use the progress or progress ratio controls to have our object move automatically along our curve. The progress value lets us place our object based on the actual distance from the start of the curve, while the progress ratio slider uses the normalized equivalent, so it goes from 0 at the start of the curve to 1 at the end of the curve. So now let's see how to apply all this to our specific use case, because actually we can quite simply transform our scene to use this exact method. First of all, to define our path, we can take our enemy's node that is currently a node 2D in hierarchy and change its type to path2D. If we reselect our node, we now see the path editing tools at the top of our viewport panel, where we can edit, add and remove points, and so we can simply click in our 2D viewport to place or edit points and set up our wave path like this, for example. If you want to get some curves and rounded corners like this, you need to make sure to switch to the Curve Control Points tool at the top and then click and drag on your different points to actually see the handles and move them to define the curvature of your path. Now let's open the enemy scene I prepared and modify it slightly to allow our enemies to move along our path. Again, we can simply change the type of our root node to pathFollow2D, and you see that Godot shows us a warning saying that a pathFollow2D node only works as a child of a path2D node, but this is actually fine since, ultimately, our instances of this enemy scene will be put as children of our enemy's node in the main scene, which we just turned into a path2D node. Also, because we want our units to walk the path once and then stop at the end, we should select our new pathFollow2D root node and toggle the loop option off. This way, the object will move forward, and when it reaches the end of the curve, it will stop at the extreme position. Finally, let's click on the script icon on the root of our enemy node to open the attached script. This is the enemy C# class with a bit of startup implementation, and that we need to upgrade to also have our character move as time goes by. For now, there's just the initialize method that we called earlier from our wave manager that sets up some variables in our script. So let's use the process built-in Godot hook to execute logic continuously while the scene is running, and in here we want to tell our object to move forward by increasing its progress or its progress ratio value. However, if we try to access any of these variables, you see that the IDE doesn't show any autocompletion, and if we were to compile, Godot would crash on us and say it's not possible. That's because, so far, we've changed the type of a node in the editor, but we didn't tell its script that it should now inherit from the pathFollow2D class as well. If we change this, then the IDE will know that our script has a progress or progress ratio property, and will be able to move our object. Usually, I rather use the normalized progress, so progress ratio, because I find it easier to control the movement of my objects when I'm in the 0-1 range. But you can of course do the same with the progress value just by changing the speed a little. Anyway, here, let's say that every time our progress function runs, we increment the progress ratio a little bit. We'll use our speed variable and multiply it by the time delta. Of course, you remember that when we defined our data earlier, we set the speeds to be numbers like 1, 2 and 3. So if we apply it directly as is, since our progress ratio is normalized between 0 and 1, our units will basically teleport to the end of the path instantly. So that's why we should actually remultiply by some arbitrary small factor to make sure it is properly remapped to a better range. And that's it actually. If we replay our game, you see that as soon as an enemy is spawned on the path, its process logic kicks in and it starts to move more or less slowly on the path, following the exact shape of the curve that we defined earlier. So you see that in Godot, thanks to the path and pathFollow nodes, it's super easy to create this kind of path constraint movement. But of course now we still have one last feature to take care of, which is checking whether the wave has ended or not, to stop our timer and prevent our logic from trying to spawn non-existent enemies. In tower defense games, there are usually two ways an enemy can end. Either it is killed by one of the player's towers, or it exits the scene and thus costs the player one or more life points. And a wave ends when all of the enemies inside its reference list have been spawned and have ended one way or the other. Of course, here we don't have any towers, so instead we see that every time we click on an enemy, it loses a life. So if it has 1 health point, it will die instantly, else we'll have to click on it several times to actually kill it. And in any case, when it exits the screen, we'll consider that it has ended. Note that in this tutorial, we won't take care of creating a global life count for the player, so an enemy exiting the level won't actually have any impact other than reducing the wave counter. But you could do it quite easily by using some game manager script, or even an autoload with global variables, as we discussed in this previous video of the series. Okay, so first of all, let's come back to our wave manager script, and at the top, add a new integer variable called wave count. We will initialize it when we start the wave by taking the size of our temporary spread list. This is the number of units that will be spawned by the manager for this wave, and when it reaches 0, we'll know that this wave has ended. So let's also prepare a public function called endEnemy that receives the reference to a node. This node will be the enemy to remove, so we'll simply call q3 on it to delete it from the scene, and we'll also reduce the counter by 1. If our counter reaches 0, we'll stop our timer, cause the wave will have ended. Now we just have to call this function when our enemy object reaches the end of the line, or when we click on it and it has no more health points left. For the reach the end of path logic, it's really easy. We only have to go back to our enemy script, and in the process function, check if the progress ratio is equal to 1. Remember that this can happen since we match it to toggle off the loop property on our path follow to the node in the editor, and so our node will stop at the end of the path. So if we've reached 1 in our normalized ratio, meaning that our object is exactly at the end of the path, we'll get a reference to a wave manager and call its new endEnemy function by passing in our own object. In order to get this root node easily, we can use Godot's absolute node path system, where we start by a /root prefix, all in lowercase, and then we put our actual node path in scene, root included. This tells the engine to start at the very origin of the current scene, and then go through it as usual by traversing child nodes. Again, it can be better to cache this reference when the script is first instantiated. So let's move this getNode call to the ready function of our enemy class. Now the only thing left to do is to check whether we clicked on a node. And because we're using 2D nodes, Godot again provides us with some super easy to use tools. Because if we go back to our scene and select the area 2D node I prepared beforehand in the enemy hierarchy, then in its signals list, you see that we have an input event signal. This is typically a very quick way of getting a click, a mouse move, a mouse enter, a mouse exit, basically any kind of input signal that happens on our node. So we'll just prepare a new callback function called onClick with matching input parameters in our enemy script, and inside we'll check if our input event is indeed a mouse click with the left button, and in that case reduce the health points of our enemy unit. If we reach 0 health points, we'll call the wave manager's endEnemy function. Then finally we'll recompile our project and link the input event signal to our new onClick function. And here we are. If we run our game again, you see that now we get our first wave with the enemies walking along the path, and we can either click on them to have them disappear, or let them exit the level and be auto-removed. By the way, as we mentioned in this previous tutorial of the series, don't forget that if you want to examine the state of the scene live while the game is running, you can always go back to the editor in the scene panel in the top left corner switch to the remote mode and inspect your hierarchy on the fly. Typically here is that when an enemy gets to the end of the path, or when we click on it, it's removed from the list of children of our enemy's node. So there you go. You now know how to set up a very basic system of enemy waves for a 2D top-down tower defense game that spawns units regularly thanks to a timer and moves them along an arbitrarily complex path thanks to a path followed to the node. If you enjoyed the video, feel free to like it and subscribe to the channel to not miss the next ones. And of course, don't hesitate to drop a comment with ideas of Godot tricks that you'd like to learn. As always, thanks a lot for watching, and take care.